Okay, so welcome to the last portion of this lecture. We're going to finish up talking about something what's called the motor homunculus. We're going to talk about monitoring the motor program and a little bit about our somatosensory area, and then wrap up with the cerebellum. So a motor homunculus, what is this? You probably have heard of this in other courses, but if not, I'm going to explain to you what it is. The primary and premotor cortex are topographically organized into what is known as a motor homunculus. This shows you that there are different clusters of neurons depending where you are on the motor homunculus. It is a funny word. Say it 3 or 4 times in a row and you'll get your tongue twisted. It says it takes many more, ultimately what it's saying is that it takes many more neural signals to what's going to activate what happens in the hand and in the face compared to the large musculature of the back, legs, and chest. The reason being is we need more motor control in the hands and face and tongue, so it necessitates that we have a significant amount of clusters of neurons that are going to regulate those areas. Okay, so again, this shows you, this is kind of a little kind of drawing or graph, which kind of looks a little funky, but this shows you that there are different clusters of neurons depending on where you are on this graph or this motor homunculus. So it ultimately is showing that there's many more neural signals to what's going to activate something in the hand, face, and in the face compared to large musculatures like the back, legs, and chest, or the trunk. Again, because all this is all related to motor control. We need a lot more motor control to manipulate the hands, the face, and the tongue than we do in the trunk itself, or within our postural muscles. So here we go. Here is the this little diagram, which is our motor homunculus. So you can see the size of the anatomical parts are showing you how much motor control needs to be given to those. So you see that the eyes are pretty big, that the ears are small, that you have like the nose and the mouth and the chin and the face is very, very large, and the lips, because this requires a lot more of ultimately fine motor control. And here, and of course our hand as well requires a lot more fine motor control. So we have those cluster of neurons are a lot bigger in this section for the most part that handle digital manipulation. And then we go over here, things with like the trunk, the legs and stuff get a little bit smaller. We don't need as much control. Okay, so moving on, monitoring the motor program. So once a motor program has been picked, we are constantly monitoring whether the program is being executed properly. So we think we picked a correct motor program, but then we have all these systems of checks and balances for the most part to make sure we are carrying it out appropriately and if it's the correct one we should be using. So this means we have to receive sensory information to the somatosensory area, and we will receive sensory info about what is happening with that motor program. So there are 3 specific types of receptors that are going to project afferently to that somatosensory area. And again, we're going to go over these. 1, they are the muscle spindles, and those respond to stretch. 2 are joint receptors. This gives us info relative to how much activity is occurring within a joint. And then 3 are cutaneous or our skin receptors. Skin is being obviously continuously stretched and compressed, and that information is going back to this area as well. These 3 receptors are being monitored throughout the entire program. So this gives us the ability to make decisions on the fly, and it also gives us the ability to correct that motor program if need be. So let's talk a little bit about the somatosensory area. When the somatosensory area receives feedback from those proprioceptors we just talked about, the changes that are going to be made to that motor program are going to be in 3 areas. 1, the range of motion. Is it correct? 2, the amount of force being generated. Is it adequate enough? And 3, the rate of shortening. Those 3 will be primarily dealt with by the primary motor area and the premotor area. The supplementary area deals with posture and our axial muscles. So, for example, throwing a baseball requires both postural and lateral control. So this area works in concert with the other 2. So we will need to work with our supplementary area on our axial muscles as we throw a baseball to keep us upright and for trunk movement, as well as it would work with the other motor areas in order to execute the throw from our arms and our hands for our limbs. Okay, so going on to the cerebellum and its involvement a little bit. This is involved mainly in postural control. It's made up of white and gray matter. This works in coordination with the basal ganglia on motor programs and process some sensory information too. So again, this is a little bit of our checks and balances too. The sensory information comes from two types of afferent fibers that are processed within the cerebellum. One are climbing fibers and two mossy fibers. These fibers are the sensory afferent fibers that project information to the cerebellar cortex. And what the cerebellar cortex does is that it's then going to be involved in maintaining our upright posture or our postural reflexes. So again, cerebellum, you might know about like a little bit about balance and so forth, and that's true. And that's how it just does so, by these different types of fibers. Okay, our cerebellum has three parts. Our archaeocerebellum, this is closely related to our vestibular system, so the major control of upright posture, and this coordinates hand-eye movement together, actually. Our paleocerebellum receives organized information from our spinal cord and will assist the archaeocerebellum with regards to upright posture, muscle tone, movement, and balance. So this helps assist the archaeocerebellum. And our neocerebellum is the most dominant portion of our cerebellar cortex. This works closely actually with our cerebral cortex and works in concert with the basal ganglia with regards to monitoring motor programs. Here we go. You want to take a look at this is a picture of cerebellum. We have our paleocerebellum is up here, and we have our neocerebellum, and then back here we have our archaeocerebellum. And again, our archaeocerebellum is the one that does major control of upright posture, coordinates hand and eye movement together, related close to our vestibular system. Paleo, up here, receives organized information from our spinal cord, will assist the archaeocerebellum with regards to upright posture, muscle tone, movement, and balance. And lastly, our neocerebellum, which is over here, is our most dominant portion of the cerebellar cortex, and works closely with the cerebral cortex and with the basal ganglia with regards to motor programs. Okay, so that was a lot of information over this whole lecture 6, which we talked about skeletal muscle mechanics, and then we segued into the physiology of motor control, which we talked about the spinal cord, and then motor programming, as well as how we control those motor programs and the different tracks. There's a lot of information here, and hopefully we'll get to review as well together in the near future. Okay, thanks. Bye, everyone.